Picture this. You're on a spacecraft orbiting a potentially habitable planet in which the best course of action is to teleport to the surface to investigate for yourself. But what if I told you that Scotty beaming you up wasn't so simple? Welcome to the world of quantum teleportation.
The only problem is that this isn't real teleportation, but it's as real as we can get. That's because instead of teleporting a physical object, you're teleporting pure information at an atomic scale. Our goal is to teleport a qubit, or a quantum bit of information, from one location to another. Qubits are usually both waves and particles, things like electrons and photons. Light. What distinguishes these from a normal bit of information is that instead of being a 1 or 0, qubits can be in a state of superposition where they are simultaneously 1 and 0 as long as they aren't disturbed by observational equipment which will collapse their waveform. The 1 or 0 for qubits is also not an on or off signal, but a spin up or spin down state of being. You're basically tracking the orientation of the 3D particle. While in superposition, depending on how they're measured, a qubit usually has a 50-50 chance of becoming a 1 or 0. Now the really cool thing about these qubits is that they can become entangled. You can think of entangled particles as a pair of identical twins. They are most often split from one initial particle, but they do have another odd property. They have a common state of either both being in the same state or both being opposites. But upon measurement and collapse, what happens to one particle happens to the other instantaneously no matter how far apart they are. So if we're using two entangled qubits, which will always be opposite, if we measure one on one side of the galaxy to be spin up, we will know instantaneously that the other will be spin down upon measurement every single time. This is what's vital to teleportation. You're basically cutting and pasting the unknown and arbitrary quantum state of one particle to another one. Say you've got two entangled particles. Particle A kept on your ship and particle B sent to the surface of the planet you want to teleport the unknown quantum state of particle C to. The first step on your ship is to perform a Bell measurement on particle A and C. You can think of it as multiplying the two together. The measurement doesn't reveal C's state, but since B is identical to A, by sending the data from the measurement to particle B on the planet, those at the station there can convert B into C, kind of like balancing an equation.
However, because you can't describe a particle's state in its entirety due to fundamental quantum mechanics, the original particle C has its state destroyed because you can't have an identical copy of an arbitrary and unknown quantum state. So compared to pop culture teleportation, it's like vaporizing someone at one station and having them reassembled at a receiver station. But unlike that example, quantum teleportation obeys relativity. That's because the Bell measurement data has to be sent to the receiver station at the speed of light or slower in order for replication to occur.